Hello, बच्चों. Welcome back to chemistry class. Today, we explore the fascinating world of isomerism in coordination compounds. Have you ever seen identical twins? Same face, same height, but different personalities. That's exactly what isomerism is in chemistry. Compounds may have the same chemical formula, but they behave very differently because the arrangement of atoms is different. Some may even have opposite properties. For example, one form of a coordination compound saves lives as medicine, while its twin does nothing. A very famous case is the anti-cancer drug cisplatin, written as cis-platinum with two ammonia ligands and two chloride ligands. This works. But its twin, transplatin, written as trans-platinum with the same two ammonia and two chloride ligands, is not effective. Isn't that amazing? So, let's dive into the tricks played by isomerism. Alright, bachcho, now that we know what isomerism is, let's classify it. Imagine this, you all have the same exam paper, but some of you solve it step by step, and others use shortcuts. Same paper, different approach, right? Chemistry works the same way. The first big family is structural isomers. Here, the bonding of ligands changes. For example, sometimes a ligand sits inside the coordination sphere and sometimes it's outside as a counter ion. This gives us ionization isomerism. Sometimes, a ligand can bind in two ways, like the nitrite ion, written as nitrite minus, where it can bind either through nitrogen as nitrite or through oxygen as onitrite. That's linkage isomerism. We also have solvate and coordination isomers. In simple terms, structural isomers differ in how atoms or ligands are connected. The second big family is stereoisomers. Here, the bonds remain the same, but the arrangement in space is different. It's like rearranging benches in your classroom, same students, same number, but different seating. Under this, we have geometrical isomers like cis and trans, and optical isomers which behave like left and right hands in a mirror. And here comes the interesting part, bachcho, even though two isomers have the same chemical formula, they can behave totally differently. One may be blue, another green. One might dissolve in water, the other might not. The most dramatic example is cisplatin, written as platinum open square bracket ammonia to close square bracket chloride to close square bracket, which can save lives, while transplatin, written as platinum open square bracket ammonia to close square bracket chloride to close square bracket, has almost no effect in the body. So remember, isomerism is not just about formulas on paper, it literally decides how molecules behave in real life. Okay, bachcho, let's jump into geometrical isomerism. Imagine your classroom. If two students sit next to each other, that's cis. If they sit opposite, that's trans. Same goes for ligands in coordination complexes. Take platinum with two ammonia and two chloride ligands, written as platinum open square bracket ammonia to close square bracket chloride to close square bracket. In the cis form, the chlorides are next to each other. In the trans form, they sit opposite. That's geometrical isomerism. Now, let's look at octahedral complexes. For cobalt with 4 ammonia and 2 chloride ligands, written as cobalt open square bracket ammonia 4 close square bracket chloride to close square bracket positive 1, you can have cis or trans arrangements depending on whether the chlorides are next to each other or opposite. And here's a twist, facial and meridional isomerism. In a complex like cobalt open square bracket ammonia 3 close square bracket nitrito 3 close square bracket, the ligands can arrange themselves in two ways. In facial isomerism, all nitro groups sit on the same face of the octahedron. In meridional isomerism, they sit along the meridian, like sitting in a straight line or zigzag. So, bachcho, geometrical isomerism is all about how ligands are arranged around the central atom. Small changes, big effects. Now, bachcho, let's enter the world of mirrors, the world of optical isomerism. Have you ever tried wearing your left shoe on your right foot? Doesn't fit, right? That's because left and right hands, or shoes, are mirror images but cannot be superimposed. The same thing happens with molecules. We call these mirror image forms enantiomers. So what's the test for chirality in chemistry? Simple. If a compound rotates plane polarized light, it shows optical isomerism. One form rotates the light to the right, that's called the dextro form, written as D-. The other rotates light to the left, that's the levo form, written as L-. A famous example is the complex cobalt with 3 ethylenediamine ligands, written as CO open square bracket E and close bracket 3, charge 3+. This exists in both D and L forms. Another nice example is platinum with 2 chloride and 2 ethylenediamine ligands, written as PT open square bracket Cl2 open bracket E and close bracket 2, charge 2+. But here comes the twist. Only the CIS form is optically active, the trans form is not. So it's like this, if the ligands sit adjacent in the CIS arrangement, the molecule becomes chiral, but if they sit opposite in the trans arrangement, no chirality at all. So bachcho, optical isomerism is like chemistry's way of showing us that even molecules have right-handed and left-handed personalities, and just like in real life, left and right behave differently. Alright students, let's jump into one of the most fascinating parts of coordination chemistry, structural isomerism. Now, what does that mean? Basically, the same chemical formula, but different structures and hence different properties. Just like two people with the same name in your class but completely different personalities. First type here is linkage isomerism. This happens when a ligand has more than one possible donor atom. Such ligands are called ambidentate ligands. For example, the complex written as open bracket CO NH3 no to close bracket Cl2. Here, the nitro group can attach either through nitrogen, giving the nitro form, or through oxygen, giving the nitrito form. So the same compound can exist into different versions just by changing the binding atom. Isn't that cool? Next comes coordination isomerism. This occurs when ligands swap places between the cationic and anionic parts of the complex. For example, open bracket CO NH36 close bracket open bracket CrCN6 close bracket versus open bracket CrNH36 close bracket open bracket CO CN6 close bracket. The ligands have exchanged their homes, like the students swapping hostel rooms, but the overall building remains the same. Now, why does this matter? Because these isomers don't just look different, they actually have different colors, different stabilities, and sometimes even different reactivities. That's why studying isomerism is so important. It explains why the same formula can give us compounds that behave completely differently in the lab and in real life. Alright, bachcho, let's look at two tricky types of structural isomerism, ionization and solvate isomerism. First, ionization isomerism. It's like a musical chairs game between ligands inside the coordination sphere and counter ions outside. For example, cobalt with ammonia and sulfate can swap with cobalt with ammonia and bromide. Same formula, but they give different ions in solution, so they behave differently chemically. Next, solvate isomerism or hydrate isomerism. When water is involved, it's about whether the solvent is inside the coordination sphere or outside in the crystal lattice. For example, chromium with water and chloride can rearrange, changing both color and identity, violet to green. The takeaway, these isomers behave differently in solution, even though they have the same atoms. Same ingredients, different effects. That's the magic of isomerism. Alright, bachcho, quick recap. We learned about isomerism in coordination compounds. First, stereoisomerism, geometrical, CIS trans, FSE mer, and optical, enantiomers. Then, structural isomerism, linkage, coordination, ionization, and solvent types. Think of it as a chemistry buffet, same ingredients, different styles. Why does it matter? Isomerism isn't just theory, it impacts real life. Like cisplatin, where the CIS isomer fights cancer, but the trans is almost useless. Colorful salts, isomers, catalysts, they need specific isomers to work. Even medicines depend on the right isomer to work in our body. The takeaway, same formula is not equal to same behavior. Just like the students with the same books, one aces the exam, the other sleeps in class. That's the power of isomerism, small changes, big effects.